Let's talk about the Biot-Savart law of finding magnetic field at any point in space near a current distribution. Now, in my notes, I also talk about isolated point particles moving and creating a magnetic field. Well, we'll focus here on just commercial wires and currents through them. So let's suppose you have a stretch of wire with some conventional current, that is current carried by positive charges, called I. Now the question is, what is the magnetic field in both magnitude and direction at P? Now Biot-Savart answered that. Now, by the way, they are French names, so you're supposed to say it as Biot and Savart. By considering elements, so you have here in the wire small elements, we'll call it ds, and ds becomes a vector by inheriting the same direction as the current direction. So the direction of ds is actually like that. You have this little ds vector, and now you have to also draw another vector that tells you where you are in relation to P. So this is sometimes called the observation vector. So you go from the for the observation vector, you have to go from the point P to the place where you're looking at. Now you're observing it at this point, so the effects are going to be felt there. So if you think about charges, that'll give you a clue of how this vector should be drawn. If you have a charge here, the electric field will point away from it, so the vector must be drawn in this direction. So for magnetic fields, it's just like electric fields, so the vector has to be in that direction. All right, so we have all the ingredients we need. Let's call this physical distance r, and we can write down Biot-Savart law. That law states that the incremental magnetic field, or the infinitesimal magnetic field at point P in both magnitude and direction, is given by mu naught over 4 pi times I ds cross r hat over r squared. There's only one or two similarities between the electric case, which I'll write here for comparison. The electric field dEP, suppose there was a point charge sitting over there, dEP would be k dq over r squared. Now the presence of the constant k, which is 1 over 4 pi epsilon naught, is kind of like the presence of mu naught over 4 pi, so that's understood. R squared, so that decay the same way. But what's interesting is the numerator. The numerator has got an amazing structure. It's a cross product of two things. So the magnetic field occurs perpendicular to both the plane of the wire and to the observation vector. In other words, it's going to be either out of the page or into the page. So let's figure out the direction as drawn here. R is towards me this way, I'm standing there, and ds is this way, so r cross ds, ds cross r is what I need to do. ds cross r will be into the page. So the magnetic field at this point is going to be into the page. Now there's a very nice right-hand rule associated to this, which eliminates the need for using this every time, although it's a useful thing to also use. The right-hand rule is an immediate way of figuring out the magnetic field. In fact, this right-hand rule is quite nice because it'll tell you the magnetic field everywhere in space. So the right-hand rule goes as follows. Imagine that the direction of your thumb, now thumb comes first this time, the direction of your thumb is the direction of the conventional current. Then the directions of your 4 fingers are going to be the direction of the magnetic field, which means the magnetic field is going to come out everywhere from there and go in everywhere here. So the advantage with this right-hand rule, which I'm very fond of, is that it gives you the magnetic field not just at one point, but everywhere in space. And furthermore, it tells you something else. It tells you the magnetic field have to be in concentric circles, and perhaps the circles, the magnetic field strength is going to also decay based on that 1 over r squared factor. So it tells you a lot of nice things just right away. And based on that right-hand rule, you can see that I got it right here too. So that's the Biot-Savart law. Let's talk a little bit about the constant mu naught. Just like the constant epsilon naught, it's a constant of nature, and it's defined to be 4 pi times 10 to the minus 7. Now, what about the units? Well, Tesla is what magnetic fields are measured in. So Tesla meter squared, well, wait, there's a meter there too. So Tesla meter per ampere are the units. Later on, I'll give you some better units. Remember, epsilon naught, we now know epsilon naught to be equal to approximately 9 picofarads per meter. Is there something like that for mu naught? It turns out there is. It's called Henry per meter. So we'll do that later on when we study the concept of inductance. But right now, let's just keep it like that. For a concrete example, let's try to find out the magnetic field created by a loop of current, but not in the plane of the current. If you want to find the magnetic field at the origin of this loop, that is done using case 3 of the 3 cases I deal with in the notes for Biot-Savart, case 1, 2, and 3. Now, this is slightly different than those cases. I want the magnetic field not in the plane of the loop, but outside the plane of the loop, somewhere here, okay, closer to the camera. How will I find that? So let me set this up. I'll start by drawing my loop of current. And I won't really worry about how this current is maintained. It could be a superconductor, for example. And I'll only indicate the current in the side that's closest to me. So you'll realize that this side is closest to me and that side is far away. Okay, now how is it that we're going to draw the field vectors? So let's set up the axes. That's the z-axis, and the point P is over here. We have to find out the dB vector, and now symmetry can be used in this case because this ring has got a circular symmetry, or cylindrical symmetry rather. So this dB vector, ds vector, comes out like this here and goes into the page like that there. Okay, so technically I should draw the ds vector as coming out of the page, which means like that, and into the page, which means like this, just to be more precise. So that's the ds vector, and that's the ds prime vector. Because we're going to use mirror symmetry, I'm going to call them the unprimed and the primed quantities. Now, the other thing we need to do is fix the observation vectors. The observation vector from the ds point of view will be here, and the observation vector from the ds prime is going to be here. And let's call the actual magnitude simply r. Let the radius of the circle be capital R, and so the relationship between rz and capital R is by the Pythagorean theorem, r squared equals r squared plus z squared. Let's also go ahead and define the angle theta for later use. Now what we'll do is actually figure out the direction. So we can do it 2 ways. Well, let's first use the Biot-Savart law. ds cross r hat. ds is coming out of the page. Let me indicate that using a pen here. It's coming out of the page, and then you have r hat here. So ds cross r hat. So it's going to be some vector in this direction. Well, that's the wrong place for it. The right place for it is here. So I'll draw a vector there. Remember what the cross product means. It means that the vector that you get, which I'll call dBp, is going to be such that it'll make a 90-degree angle with both the r hat vector and the ds vector. The fact that it makes a 90-degree angle with the ds vector is obvious because I've drawn it on the page while the ds vector is coming out of the page. But here you have to make sure that 90 degrees is maintained between r hat and this dB vector. By the same logic, and let's see if this, by the way, jives with the right-hand rule. I have the wires coming out of the page, so the current's coming out like this, and the magnetic field is sure enough in that direction. how about here? The magnetic field will be in this direction. So beautifully we can find out both of these things quite easily. That's dB prime. So that's one of the big differences between electric field and magnetic field. If this were a charged ring, okay, the electric field of the charged ring would be a continuation of this thing. Well, that is not the case with the magnetic field. Okay, it's a very strange looking vector. So be very careful there. One of the common mistakes I see students making is they think the magnetic field of this is going to be straight like that, and the magnetic field of this is going to be straight like that. That will lead you to immediate ruin. So now let's figure out what's going to happen. By symmetry, that's all theta, and clearly the sine components are going to add up, the cosine components are going to cancel out. So we can set up our integral next. The net magnetic field dB net is going to be 2 times the value of dB times sine theta. Well, dB is given by that in magnitude, so that's going to be 2 times mu naught by 4 pi I times ds. Now for circular geometry, let me just write that first though. ds times the magnitude of r hat, which is 1, times the angle between ds and r hat, which is 90 degrees, over r squared, which is just little r squared, times sine theta. Okay, now ds can be looked at in the following way. If you have a circle and you have this ds and this is r, and let's call this angle, because I've already used theta, let's call this d phi, then the relationship between ds and d phi is ds equals r d phi. We're going to be using that, where phi is the coordinate along the ring. Applying circular arc logic, so I'm going to get 2 times mu naught by 4 pi I times r d phi divided by r squared. Sine theta is next. Sine theta is, actually it's this way, so you have to turn your head a little. It's opposite, which is r, divided by the hypotenuse, which is little r. Great. So we have done everything that we need to do. So that's going to be mu naught over 2 pi I r squared over r cubed d phi, and that's dB net. The reason I did not bother substituting for little r yet is to show you that this expression has got very little calculus in it. The only variable is phi. Z is not a variable. I'm holding the point P fixed. And if Z is not a variable, then little r is not a variable either. So the calculus is very simple. The total magnetic field is going to be the integral from where to where. That's where you need to be careful. I have taken just the mirror symmetry elements already, so I can only go halfway. So it's going to be from phi equal to 0 to phi equal to pi of dB net. And when I perform this integration, it's not even worth writing. The integral of d phi is just phi, and when I evaluate phi between the limits, I'm just going to get pi. So I'll get mu naught by 2 pi I r squared over r cubed times pi. That pi will cancel this pi, and now I can go ahead and maybe substitute for little r. Little r is r squared plus z squared to the power half, so that's going to be 3 halves. And that's the magnetic field at the axial point of any current carrying ring. This is a very useful result, and we're going to apply this to the concept of the magnetic field created by Helmholtz coils in one of the labs. In one of the labs, we'll have a chance to work with these coils known as Helmholtz coils. There are 2 current carrying coils separated by a certain distance, and we're going to have a electron gun placed in a evacuated bulb in between them, and the magnetic field at this point has to be calculated due to this Helmholtz coil and that Helmholtz coil. Well, this is exactly the setup of this problem. So we have to use the distance z, which is half the distance between those two coils, as the distance. Of course, we also have to use a number of turns. This is for one turn. For n turns, you just multiply the whole thing by n. The last order of business is to show you that this results in the same as value as case 3 if I bring z to 0. So in the limit that z goes to 0, what do I get of b net? Well, if z goes to 0, that just becomes r cubed. So I'll get mu naught I over 2r. And this is indeed case 3 for the loop.